So hello everyone, today we're going to be doing another little nice bit of calculus. Namely, we have this linear or curvilinear integral, which is the integral over the curve c y ds, where c is the arc of the parabola y squared is equal to 4x, which is cut off by another parabola x squared is equal to 4y. Okay, so how do we solve these integrals? And is there some maybe formula? Of course there is. So the integral of curve C, the integral over curve C of some function of xy, of x and y ds is equal to the integral from a to b of f of x and y of x times the square root of 1 plus y prime squared dx. Okay, so with that in mind, the best way to show you how to do these problems is to do them ourselves. So first we want to find our limits of integration. Okay, so let's just go ahead and find the intersection points between these two parabolas at first. So y squared is equal to 4x and x squared is equal to 4y. So from here it follows that y is equal to x squared over 4, and when we square both sides we'll get that y squared is equal to x to the 4th power over 4 squared, which is just 16. So when we go ahead and plug that into our first equation, we'll get that x to the 4th power over 16 is equal to 4x, or x times x to the 3rd power over 16 minus 4 is equal to 0. So from here it's clear that x1 is equal to 0. That's the first case. Or x to the 3rd power over 16 is equal to 4. Therefore, x to the 3rd power is equal to 64. From here, we get that x2 is equal to 4. So these are going to be our limits of integration. Okay, so now we take our curve C and say that, and we know that y squared is equal to 4x, so when we take the square root of both sides we'll get that y is equal to 2 times the square root of x. So when we differentiate this part with respect to x, we'll get that y prime is equal to 2 times the derivative of 1 under the derivative of the square root of x, which is just 1 over 2 times the square root of x. 2 and 2 cancel out, and so y prime is equal to 1 over the square root of x. Now that we know this and that we know this, we're going to plug in these into our formula, and then we'll get that the integral over the curve C of y ds s is equal to the integral from 0 to 4 times, now instead of y, we want to express this y right here as a function of x, as a function of x. But how do we go about doing that? Well, it depends on the given curve c. And this is the equation of our given curve c. So we'll get the integral from 0 to 4 of 2 times the square root of x over, and this is the other part of the formula, this is this part of the formula, of 1 plus y prime squared, which is just 1 over the square root of x squared, which is, okay, just 1 over x, and of course everything times dx. Okay, so we can factor out the 2, and then we'll get the two integrals from 0 to 4, and we can put in this square root of x right here, and that will give us the square root of x plus 1 dx, which is really the same as 2 times the integral from 0 to 4 of x plus 1 to the power of 1 over 2 dx, which will give us 2 times x plus 1 to the power of, we add 1 to the exponent, of 3 over 2 over 3 over 2, which is, and of course, between the limits of 0 and 4, which is equal to 4 over 3 times x plus 1 times, okay, I'll rewrite it in a slightly different manner, times the square root of x plus 1 to the third power. We're still between the limits of 0 and 4, and this is equal to 4 over 3 times 4 plus 1 is equal to 5 to the third power is 125, which can be rewritten as 5 times 25, so this will just be 5 times the square root of 5, minus, when we plug in 0, we'll get just 1. Okay, so this is the solution to our problem. Now, and I'll also say that this is our final answer to the given problem. However, what I also would like to do is tell you the meaning, the geometric meaning of the value of this linear integral, not just this linear integral, but pretty much all of the linear integrals. So I'm just going to go ahead and draw our standard 3D XYZ system. So this is the x-axis, this is the y-axis, and this is the z-axis. So let's say that we have some curve in the xy plane, and let's say that the equation of this curve is y is equal to f of x, or instead of that we can just write it as y of x. So the equation of this curve is some function of x, and this curve lies in the xy plane. So, and when we go ahead and let's say that we have some arbitrary surface above the xy plane, and I'm going to go ahead and do my best to draw this nicely for you. Okay, this is a bit hard, but hopefully you'll get the idea. Okay. And now, what we're actually trying to compute is this, is the surface of this. It's almost like a curtain. So we're trying to compute the surface of this curtain. And of course, the function of this arbitrary, okay, in a given problem it won't be arbitrary, but in the general case it is. The function of this surface right here is z of x and y. And of course y is a function of x. So when we look at the projection from the top, okay, so when we look at the xy plane from the top, we can see that it's going to be something like a weird 3. Okay, so this is the x-axis and this is y-axis. How are we going to compute the surface of this part? Well, as I drew it right here, we're going to split it into a lot of these small parts which have the size ds, that's their width, and which have the height of z of x and y at that place. And of course, when we're looking at this part right here, let's say, okay, and imagine that this is infinitesimally small, dx and ds. This is our ds, okay? The red part is ds. Well, we can break it up as, well, we can break it up in this manner. So, and by using the Pythagorean theorem, we have that ds quantity squared is equal to dx quantity squared plus dy quantity squared. So from here, ds is equal to the square root of dx squared plus dy squared. Or when we factor out the dx, we'll get 1 plus y prime, which is the same as dy over dx squared, and everything times dx. So that's basically the width, this here width, right? And the height of this small rectangle is going to be z of x and y. So that's just for one of these rectangles. That's just for one of these rectangles, and the area of one of these rectangles is going to be its height, which is z of x and y at that point, times its width, which is just 1 plus y prime squared dx. And since we want to compute the entire area, we're going to have to integrate from a to b, and a and b are these limits right here. Okay, so this is a and this is b. Okay, so I hope I gave you a little bit of an intuitive understanding of this here problem, the meaning of the curvilinear integral, and I hope you enjoyed the video. If so, leave a thumbs up and subscribe. I'll see you in the next one, and goodbye.